Can. All right, can. So y'all can still see my the Microsoft Word, no?
Yes.
Okay, good. So I started the recording, so not to worry. I will share with you once it's done. Okay, so what happened is that because in the oscilloscope, okay, now of course there's this piece of breadboard here, you're supposed to draw, but it's quite impossible to what do you call that? Yeah, we can't do the breadboarding here, right? What I can show you is the layout, the two components here. So basically there are two 1K resistors in parallel, right? And you have the other 1K here. This 1K at the bottom on the right hand side there, right? Basically it's just for us to monitor the voltage drop, so that if we put on the oscilloscope the channel 2, let's say, you can see the voltage across this part here. All right, and of course the two 1K resistors when they parallel, right? So we know that when you have two resistors in parallel, you actually will halve the resistor value. So you basically effectively you only have a 500 ohm resistor. Do you all agree?
Yep.
Okay. So basically, if you put a differential probe across using, let's say, CH1, CH1 stands for channel 1. Then you have the plus and the minus. I believe you all know what is a differential probe, right? You'll use some scope before, right? I believe. Right, I think so. You all should have used. So basically, so I think very clear cut is that in this example here, because it is resistive circuit, and according to Ohm's law that we know very well, where this ET is the signal source, and then of course you got the VRT, right? Is the voltage drop across the single resistor, which is the channel 2. Okay, so because these are resistive circuit by nature, this one resistive, so it's pretty simple, because it is resistive circuit, right? Now I'll skip the breadboard part, no need. Okay, the resistive circuit, right? And we know that Ohm's law tells us that V equals to IR, right? So ideally is that the voltage and the current will be in phase. Am I right? This one is the very simple. I think you all know this already, right? So this part I help you all first. Okay, so can you all quickly take note? Okay, for the voltage and the current for resistive circuit, no phase difference. Can?
Oh, got people break fast.
Or is it somebody? 708. Okay, those are Muslim friends. Y'all need to break fast. Y'all go ahead. But maybe I suggest you don't leave the room. Keep the system locked in. No sound. This Miss Chu. Just now you say what? No sound. 640. Oh, that was just now. Sorry, I was looking at the past messages. Make sure y'all can hear me. Okay, so the first part, can you all please take a look first? First part, no issue, the resistive circuit. So I tell you what I'm going to do is that, okay, by right, okay, this one is the solution. You're supposed to sketch, sketch yourself. So in the case, maybe I don't show you the second part, you all will need to work out. So the idea is that for the, continuing the first part, right? Yeah, so because in the oscilloscope, you all know that the screen, right, the oscilloscope screen will be, actually you're not supposed to see this, like you would see like this, right? If it's a sine wave, okay, you will see this red one, this particular screen one. All right, because it's the voltage and the current are in phase. Okay, but you all need to decide on what is the vote per division as well as the time scale. Okay, so the one I let you all try out first. Okay, I'll stop the screen share for a while. Just let me stop the screen share for a while. Okay, who is this person? Good evening. Our friend here. Can you can you identify yourself? Your name, who is the Mr. User?
Yasin.
Oh, Yasin. Okay, can. Thanks. Yasin, we are looking at lab 2, by the way.
Okay,
Mr.
Roger.
Yasin, yeah, can
Yeah,
you can off your camera, no worry.
Okay, can.
You can switch off your video. Yasin, next time maybe you rename yourself. Miss Lee. Miss Lee. Miss Lee. Miss Lee. Yeah, good evening. Miss Lee, can I verify your student ID, please? Can you hear me? For the rest of you, help me out with the circuit. Y'all help me to sketch the waveform and put in the voltage time division. Miss Lee, can you hear me? You are muted. Miss Lee. Miss Lee, I can't hear you. Sorry. You have to, I need to verify your ID. Miss Lee, are you there? Yeah, everybody, please remember to do the attendance poll. Okay, just a reminder. Yeah, this one I cannot repeat this one many times. So you all got to help to remind each other. Miss Lee, I can't hear you also. Still cannot hear you. When you are able to speak, you speak up. Okay, so we will still have to carry on. All right, so let's go back to the screen. Let's go back to the screen. Okay, so for the first part, the scope 1, right, is the sine wave. You have two sine waves, basically, one on top of the other. Now, can you all make a guess? The one that I'm showing you. Can you all see my screen?
Yes.
Can you see two sine wave, right?
Yes.
Okay, tell me which one is the source. Can guess or not?
Blue?
Yes, why? Anyone?
Higher?
Our
Huh? Higher.
Larger? Voltage
no
is
lah.
higher.
No, not really lah. You must see the source. Take a look at the signal source. You're right lah. That's a guess I suppose, right? But why is it the blue one, not the red one? Look at the amplitude.
Red one is the current, is it?
No, what is the amplitude?
6 volt.
Peak to peak.
6 volt peak to peak, 3 volt.
Yeah, correct lah. Exactly. So it's actually given to you. If you look at the diagram there, you see here. Okay. Over here, yeah, there, 6 volt peak to peak, right? So your peak voltage is 3 volt, right? So therefore, the blue one is the voltage source. Okay. All right. So ET is your blue one. The VR is the other one, the red signal. So I hope it's clear now. So basically, okay, that is the sine wave. You're supposed to actually in the lab, what you all see is the screen one. Right, you're actually going to sketch this in the lab. Actually, what we do in the lab setting is that you will see these two waveforms. You're supposed to sketch it out, and at the same time put down the volt per division as well as the time per division. Okay, so now how do we get this time per division? Very simple. So if you see my little calculation here, right? Okay, because actually if you study carefully the oscilloscope, there are 10 boxes vertically and 10 boxes horizontally, right? So if you use 1 volt per division, you span across the vertical scale, so no issue. So and then also for the horizontal scale, the time axis, because your period is 0.8 millisecond, right? If you can see over here, the period T is 0.8. So if you span across 8 blocks, 8 square boxes or 8 division, so maybe you can use 1 division to be 0.1 millisecond. Okay, so this is how we sketch this waveform, right? And set the appropriate settings for the scope setting to derive the answer. Any question so far? Miss Lee, I still cannot hear you. Miss Lee, I saw your photo just now. You show me your this one, but I can't hear you.
What she says, she's searching for the mic.
Okay, thank you. You all try to relay that message, but I can't hear your voice. Okay. Yeah, these are the issues when we do technology, this kind of online thing. So we have challenges, but no choice. We try our best. All right. So okay. Any question for the section A? Very easy. Time domain measurement. Very, very easy. This one probably you all already know. This one. So the idea is to let you also know things like what is peak to peak voltage, V average, VRMS. Okay. Hey, what is VRMS in this case? Do you all know? What is the RMS voltage for this signal? Can ask a general question. What do you think? Anyone? Anybody know what is the RMS value?
Divided by square root 2.
What divided by square root 2? Correct. Yeah, something
6,
square root 2. Is it 6? Are you sure?
3.
I'm not sure.
Because 6 volt is peak to peak. Alright, so you're supposed to halve it first, right? Because we know that V peak equals to square root 2 times V RMS, right? Okay, so don't be careful, be careful. Don't take 6 times root 2 or anything like that. So you have to take 6 volt divided by 2 first, so you get 3 volt peak, right? Right, 3 volt peak. So in order to get the RMS, so your 3 volt peak, you have to divide by square root 2, right, to get the RMS value. So let me do for you. So if I take 3 divided by 2 root, okay, I'm using my calculator here. So what you all get? Okay.
2.12.
Okay, correct. 3 divided by square root 2, right? Yeah, so decimal number 2.12 volts RMS. Okay, okay, pretty straightforward. Can okay, so I leave it to you to go and sketch this waveform. This one, okay, this is just a sketch. Not very perfect. Okay, not very perfect, but it's good.
The breadbook sketch also, is it?
Yeah, you can sketch. If you all got print now, it's okay lah. I don't know, not easy, right? You all got printer, you all can print. If not, you all just do a quick sketch.
No printer lah.
Printer, yeah lah, same lah. I also must be careful in printing because the resources very scarce. Okay, no problem. Okay, so just do a quick one. This one. Don't spend too much time. Don't draw until very perfect. No point. That's not the idea. Okay, so just do a sketch. So voltage, current, resistive circuit. The voltage one must be higher than the other one. Okay, resistive circuit, no phase difference. Remember, no lead or lag. Look different, no range. What is the rate for standard? What is that? Somebody asked. Mr. Clarence ask a question. What is the rate for standard waveform? Yes, the rate. The one is the. Just now I show you one blue, one red. Remember? The red one is the current.
Oh, noted.
Okay. Thanks. No question. We will proceed. Okay. Second part. This one. Okay. This one more tricky. Okay. If you recall, okay, this one inductive circuit, right? So what can you say something about inductive circuit? Do you all remember the word sieve?
Voltage leads current.
Very good. Somebody remember. Okay, you all learn this sieve, right? Can remember this word? Sieve. C stand for what? Anybody? C stand for
Capacitance.
very good. Capacitance, right? Then of course you got the L, the letter L at the back there is for inductive, right? Or inductance. Sorry, my typo mistake. Okay, inductance. Okay, so if you recall, let's say look at CIV. All right, we know that for capacitive, I'm gonna just put inside the little check box there for capacitive. Okay. Yeah. So it can help you. You can also, maybe sometimes the audio may drop along the way, or maybe I speak too fast. Okay, so I just type in the box. You can see. Okay, current leads what? Can you remember? For capacitance, what happened? Current leads voltage, right? Agree? Now what about the VIL?
Voltage lead current in inductance.
Very good. Thank you so much. Okay, voltage leads the current. Okay, for inductive circuit. Okay. I think you all know this one. But if it's pure, let's say you have an AC source, one AC source together with one capacitor, what is lead by how much? Do you remember? Still back to this CIV, capacitive. If it's pure, if it's purely capacitive, what happens? Can you remember? For purely capacitive circuit, you lead by how much? Lead by what? Any idea?
30
Forget already.
Forgot already, huh? Okay lah, just tell you lah, 90 degree.
30 degree.
90. Okay, if it's just a purely, imagine there is a AC source, then you the same circuit lah, but now you just put one capacitor. Okay, so if it's capacitive circuit, the current lead voltage by 90 degree. Okay, same for inductive, VIL. Okay, the inductive, okay, just to type it here. Your current, what happened? Current lags, right? Voltage by how much? Pure inductive lah. Led by how much? I think you all slowly get the idea, right? 90, correct. Okay, led by 90, very good, Okay, lags by 90 degree, very good. Okay, very good, everybody. We're trying to help you recall. Very good, everyone. Okay, now, so let's take a look at this. You're still seeing my screen, I hope, and still see my word. Occasionally, y'all can just shout out so that I can, otherwise I'll be like, yeah, thanks. You know, I'll be like talking to myself. Don't know whether got the communication still there. That is the problem. Okay, never mind. So, yeah, for this second part, okay, you can see this one, inductive circuit, same thing. Okay, but this one is there's a bit of how to say, a bit of a RL circuit . Okay, that means you have you see this is an inductor, right? You all look at the circuit. Okay, you got the inductor. What is the value? The inductor. Can you all tell me what is the value?
Milli.
100. You all can see or not?
100 millihenry.
Okay, can see. Just joking. Okay, 100 millihenry. Okay, zoom in for you. So maybe the circuit now a bit clearer. Okay, 100 millihenry. Can can see or not? Okay. Too big. Okay. Okay, 100 millihenry. But in parallel with a 1K ohm resistor. Okay. So, okay, now I'm not going to go into the detail. Actually, it's not the intent of the lab sheet to go, that means go into, the details of the mathematics. In other words, of course, you can do things like all this. Let me show you. Actually, of course, I just show you one book. You all see this book. Okay, so the intent is not to so-called dwell into the mathematics. So let me show you one. It's not to go into this one. We just give me a moment. Okay. Okay, it's not, y'all can see. It's not to go and show you all this phasor diagram, all this kind of thing. Y'all can see on my camera. Okay, I'm putting it across. Okay, it's not to go and analyze the mathematical so-called expression, and then you try to solve. You all know what's rectangular polar? You all know? You know things like impedance or not? Let me type.
Yep.
Okay. So let me just type to everybody. Okay. Now the idea is not to go and do this. Okay. I don't know whether you all remember this or not. You know what's this or not?
Yep.
You all learned this, right? I think when?
2 sems ago, I think.
Two sem. Is it in mathematics or what? You all got take one math module. Is it AC? Is it? You all learn something called?
Yeah.
AC circuit. I think taught by Madam
Last
Liang.
semester also have.
One lady lecturer, right? Madam Liang Xiping, I think.
The AC one have.
Quite an elderly lady, right? Who taught you all this one, if you remember. Was it?
Yes.
Quite a big class, right? Remember? Quite a big class. I think it's an LT one, right? Usually your class, that class.
At block 73.
Yeah, 73, one of the LT, 73A or something, I can't remember. Right.
Jumping one.
ABC.
ABC.
Yes. Okay, so is the intent, okay, the idea I want to tell you is that that one is AC circuits, just to share. That one is called AC circuits. Okay, but luckily, okay, the intent of doing this thing here is not to go and solve all this R plus J, all this kind of thing, okay? So in the lab setting, actually, if we do this in the lab, what the student need to do is to connect this circuit up, okay, and then they see the oscilloscope. All right, they will see something like this. Okay, you see my sketch. Okay, not very perfect, this sketch, but actually, you want to see the nicer one. The nicer one probably looks something like this. Screen lab 2. Something like this. This one. Can you see? This one is maybe a better picture. Okay, so you got the blue one. Okay, I think now you know smart idea. The blue one is the voltage source. Okay, the red one is the current. But the current, there is something slightly peculiar, right? Something different from just now the first screen that earlier that you saw, the resistive circuit. This one is inductive. Okay, so the idea in the lab setting here, we ask you to sketch. So basically, student connect up the circuit, they will sketch this waveform. Okay, but the point is, okay, so I'm helping you already. And this one I'm helping you, and you will notice that for this one, the it's an inductive, right? Inductive. So what happens in the inductive? So if you're CI-VIL, right? So your voltage leads the current. Am I right? Oh, correct. Voltage will lead the current.
Yep.
Okay. Yeah. Okay. Very good. So what happened is that, okay, now imagine okay, you got this waveform all right. Now of course the sketch here is very awful because as you know we use those the digital pen we all sketch this thing a bit crooked but never mind okay, so but lag by how much that's the thing. Lag by how much? Now just now I told you what 90 degree, right? But this is not the case because if it's purely inductive, okay, if it's a pure inductive circuit without any resistor, then yes, okay, there will be a 90 degree difference, right? Right. The current will lag the voltage or by 90 degree for inductive circuit. Or you can say voltage leads the current by 90, also can, right? It's a relative term. But because this is a mixture of resistive and inductive, okay, now that if you want to go and work out, of course, that's not the intent. Okay, the intent is that if you put this waveform on the oscilloscope, you will see this, and you're supposed to in the lab measure this difference. Okay. Now, question is this. Okay, let's say assuming assuming you don't have the lab, right? You don't have the scope. Okay, but what I can share you here is that, let's say, for example, if you see the waveform, right, the voltage leads the current, right? Let's say if I tell you, hey, the waveform looks something like this, but how are we going to know what is the lagging angle? How to solve? Question I throw to you all, how to know what is the angle based on the scope waveform that you see. Okay, my question okay, I type it here. Okay, my question is this. Okay, how to determine the lagging angle? We know that the voltage, right? Okay, voltage leads. Always start wrongly. Voltage leads current, right? By 90, right?
The phase different in time.
Yes. How to determine? Okay. So that's my question. Okay, something for you all to think about. No, this one. Hey, you all may cannot ask question. This one. During your, I think there's probably Mr. Chan will give you a quiz. This one. But I thought I'd share with you all first. How to determine the lagging angle? Inductive is voltage leads current, but 90 degree is if it's purely inductive, right? But because this one got resistance, right? Therefore, the 90 is no longer 90. So there will be some angle. Yeah, okay, correct. Some of you say, okay, Mr. Clarence, right? By looking at the division on the graph, you're right. Okay, so let's say assuming, okay, because you can look based on there are two methods. Okay, two ways to look at it. Two ways. You can go by time scale. Okay, put it this way. You can look at time scale. That's one. Looking at the time scale. Okay, time scale is one. Right. Secondly, you can look at the physical difference. Right now, this physical scale. That means based on the so-called the number of boxes. You understand what I'm saying? Number of boxes in the physical side. Okay. What do I mean by the boxes? You count basically. So you look at, remember, we must look at one time period of the waveform. Okay, one time period. What is the period? This one. What is the period again? It's time period. Oh, just now you all calculated already. What is the time period of this waveform? Now we calculated already.
0.8.
0.8, right? Okay, 0.8 is you must remember, you want to calculate this thing, you must go by one period, one whole cycle. You cannot do half cycle, no such thing. Because you know what, if you do one full cycle, right, one full sine wave, then your angle, we know we start from 0 degree, right? Then you will end at 360, right? The full cycle, imagine you have a sine wave, full cycle is 360 degree. So we want to find what is the lagging of the angle, right? Well, I mean, it can be, I mean, if it's capacitive, it's leading and so on. But for this case, okay, if you study my graph, what we do is that we use the other method, the so-called the physical method. That means we count the number of boxes. Okay, so in the case, let's say in this waveform, okay, there are actually how many? You go and count. 1, 2, 3, 4, 5, 6, 7, 8. Okay, how I get 8? If you look at my sketch here, how I get 8? I count physically the number of the division, the number of horizontal division, number of boxes on the horizontal scale. Okay, so there are 8. You understand what I'm saying, right? You guys, ladies, count the number of physical boxes on the horizontal scale. There are 8, but the 8 must be for one period. Remember, because one period, one full cycle is one period. One full cycle is 360 degrees. Remember what we are trying to do. The objective is to get the angle, right? Trying to find. Objective is to find angle. Find the lagging angle. Right? Okay. Find the lagging angle. Okay. In degree. Remember. Okay. So what I do is that then you find the difference between the two waveforms. The one is the voltage. The other is the current, right? And we note that for this particular case, the voltage leads the current by a certain amount. But we want to find out what is the angle. So in this case, if you study this waveform, it's actually about 0.6. Okay, 0.6. So you take 0.6 divide by the total number of so-called physical boxes. There are 8 of them, right? So 0.6 over 8, you multiply by 360 degrees. Right? You will get this particular answer, 27. Okay, so maybe you all can write down. It's so good. I basically do for you all. Correct. This one. But of course, you all don't have the scope. But you understand what I'm saying. I mean, that's the most important thing. Okay. Important is you clarify. You're not sure. Clarify. You understand. That's the main thing. I mean, to me, answer is one thing, but the important is the understanding. You understand what I say. Oh, This is how I do it. How you should measure the phase lead or phase lag. That's the key thing. Okay. So far, so good.
Yes.
Okay, very good. Everyone.
So
Oh, set.
the
Yeah.
lab, right?
The
lab 3 need to do the working inside
for which one?
for this lab 3.
This one, where got working? Oh, this one, yeah, this one. Yes, please put it down.
Okay, noted.
Try to put down this. How to get how to calculate the angle. In other words.
So you will share this document also in the YouTube, right?
No, cannot. Let me share the video with you.
Video. So we'll include this share screen, is it?
The video is, I think you record the entire screen, right? Whatever that is captured.
Yeah, technically yes.
Technically, that's the whole idea when you record the whole activity on the screen, right?
Yeah, so everything will be shown.
I suppose so. Yeah.
Okay.
Okay.
Suppose. Okay, thank you.
Can
That's good enough.
Okay. Hey, I think good enough lah. Hey, mine need greedy leh. Y'all like that how? Okay. Jokes aside, hey, y'all gotta try lah. Y'all try. Okay. Now for the capacitive one okay, I tell you okay, the capacitive one I want y'all to try yourself Okay, the idea for the capacitive circuit is the same Okay, same thing. Y'all figure out same thing. The angle okay, if you sketch okay, I'm going to sketch for you this y'all go and do for me Okay, this is the screen lab 2 screen scope number 3 correct. This one just now the scope 2 right. This is the first one okay. I'm just showing you again just now the resistive one is the first screen Then the second one is the inductive one right, which is this screen here. Okay, and then now is the third screen Okay, this one. Okay, you figure out yourself So now I just now was holding your hands. Now you all try to figure out yourself This one for the capacitive circuit same thing. Okay, now also you can consider this one the same thing the blue waveform, the blue plot is the voltage, the ET then the red one is the current Okay, so and in the capacitive circuit I think you already know I told you right, CIV right. Okay, so can you all try and do this yourself? Okay, CIV. This is my tip for you already. The rest, I think that's about it. That's quite simple. Okay, submit by when? Next week. CIV. Okay, so you all figure out the capacity one. Submit next week. Can I will put inside it's inside the same thing is in the MS team. Submit at the MS team assignment. So far, you all have been quite good. You all quite orderly. You all handle. I said maybe I think maybe one or two. I think haven't hand out. Submit at the NS team under the lab 2 lab sheet. Don't mind. Yeah.
Okay.
Can
Can.
Okay. After next week, that means okay. Wait. Next week will be tutorial, right? But after the following week will be something also more interesting. You're going to play with this thing called lab view. Okay. Hey, anybody who Mr. Lock? Do you still have problem with the lab view installation? Anyone got problem? You good to sound out, any issue with the installation? Okay, because you need to have it installed, because subsequently lab 3 onwards, we are going to use this software, which I think is a good thing because you all have the software installed, then you all can try out. How to use? Very good question, Mr. Clarence. Okay, how to use? It's an excellent question. Okay, I'm going to tell you some resources. Wait a moment. Okay. Okay, I need you guys and ladies, okay, to go to this. Okay, I stop my screen share, Can I stop my screen share? Okay, okay, I stop first. I show you this website. Just a moment. Okay, you need to help me, guys. Y'all need to let me share this URL with you. This NI website. Okay, this one. Okay. Yeah. Okay. If y'all can see my web browser.
Can see, can see.
Can see. What do y'all see?
National Instruments.
National Instrument. Very good. Okay. Now this website, right? Okay, I will run through y'all, not to worry. But I would recommend, okay, that y'all can go and take a look. There's a series of this thing called like self-paced video. Okay, you see, self-paced training video for students, and it's a lot, quite a lot. Okay, if you have a bit of time, I would recommend you to go through the first 5. Okay, so you can see there's this thing called the lab view environment. Then you got things like loop and execution, data structure, okay, blah, blah, blah. And number 5 is programming tool. Maybe I'll just show you one. So if you click on lab view environment, maybe you also can try on at your own remotely and your own machine using the link. So how do I Google search this guy? Very simple. You just Google search. Okay, you just Google search, okay, without the codes, call learn lab view. 2 words. Okay, without the codes, okay, without codes in Google. Okay, just search for learn lab view, you will come to this here. Okay, then okay, you will come to this page here, which is very, very useful and it's free. And this software is very expensive, to be honest. Okay, very expensive. The commercial one, very powerful. Okay, so let's say if I click on this, okay, learn. There's a whole host of this training video. Okay, I'm just trying to launch one. Okay, very useful. This one, yeah, he will explain to you what this software does. Okay, what are some of the features in this graphical programming platform called LabVIEW. Okay, very powerful, this software, to be honest. Okay, I love it so much, this software. Yeah, I've been, as I showed, I think I told you, I've been using this software for 22 years. Okay, so can kind of like use it to really the 探价 tool. You know, 探价. You know, and now I'm joking, right? No, you understand? Okay, it's a tool that you can earn a living. All right. So maybe if you are interested, like if some people are very good in Excel, right? This kind of skills is very powerful. And maybe who knows, you all may be very good in certain things. Some tools. Okay, so this one is my so-called one of my very useful tool in my tool bag. So-called. I use it to 探价. Okay, so I'm a trainer for this software. So-called. So I also do some consultation and training for this company, and they hire me as a professional instructor to teach this thing. Yeah. So just to share, so you all will get a chance to play around with this software, then see how applicable for you guys.
Okay.
Right. Okay. Okay. I think I will don't want to hog you already because now 7:50. You all maybe have to take a quick break and then go for your lecture. Okay. Yes. So any more question? Quick one. Any last few questions? Yes.
Just to check, can we just cut the 3 lab picture and put into the
Can. You can submit soft copy. Soft copy submission is good. You know what I mean? That means you got the Word document, right? Then you just put the thing inside. But the thing is that I want you all to explain the calculation, the angle, that one. That's the thing that I want you all to put in. I mean, the picture is not a problem, but I want you to explain how you get the angle, leading or lagging. Yeah, I understand what I mean? Yeah, stop my screen share first. Sorry, stop the screen share. You understand what I'm saying? I want you all to explain that part, the leading, lagging, how you calculate. Okay. Mr. Lau, you want to say something? Anybody? Mr. Clarence, okay? No. So far okay. So far so good. Can okay, one last thing. Okay, attendance poll. Please tell you all first. Y'all, this one must do. This one quite serious. The CET keep harping on us. Okay, attendance poll. Please do. Please go do, okay? Go and do it. Please kindly do it. Because you know why? Yeah, please do it. Yeah, because if you don't, the attendance there they not capture, then later got problem. CET will come after us, then they will come and harp at you as well. Okay, so CET will be harping at us. CET will harp at us. Okay, because that one the statistics they will track. They will capture your login and then they will track that you are inside. You got to do the online material and all those things. Oh, sorry about the survey so-called fatigue. Sorry about that. But the one I will bo pian. That one I also can't help it. Survey fatigue. Sorry. But this is not what I want. This one is the by CET. CET wants it. Okay.
Sorry, sir. Just double check with you.
Yeah.
Can for future login, can you put the link in the WhatsApp better?
No. Okay. Okay. One good question. Thank you. The reason why okay, another problem. That one also cannot. Because you know good question. The question was whether I can WhatsApp you the Zoom link, right, for the meeting. Okay. We also thought about it. I also think about it. It cannot because CET wants that link to be parked inside the polymer, and then they want to turn on the statistics. You understand what I mean? I know it's inconvenient for y'all. I am very sorry. They want y'all to go there and then you understand what I mean? Because they looking at the statistics. Because once you're logged in, you click on that one, right? They will know. Yeah. So I also want to make it convenient.
For my part, I cannot log in, sir, using that one.
The polymer.
Using that one, I can.
Then how you do the attendance poll?
He's saying the link the Zoom link.
Understand.
Zoom link, I cannot log in using that Zoom link.
The Zoom link that just now is wrong, Then you remember you share the link.
Y'all share with the group
Yeah.
Okay that's the problem. I have no solution for now. I need to put the link there. If not, I would have you think about it. I would have WhatsApp you already. What for I have to trouble to go there, right? How you understand?
No, his question is he cannot using that link to log in because the link that you send is different from the meeting now.
Understand.
So
by right, I think I
wrong
should.
link
So
next
maybe
time,
maybe
correct link. Then it's okay.
It's not my problem. I'm the one who create the problem. The link I give you maybe because I said recurring. Is it you all were saying?
I think you start a new meeting instead of starting the original meeting. So next time,
I change. Every time on the day I make one link now. I put it there, and you all try and click on that link now. Yeah, Miss Lee also still cannot hear you, Miss Lee. You say you're facing difficulty. She cannot. Yeah, okay. I think okay lah. I think the meeting will kind of end here. But if you all want to ask me question, you all can still hang around. Not our lesson end. Okay, lesson concluded. Thank you very much. Okay, Miss Lee. Maybe she will. Miss Lee, you can text me. You all got issue, right? Text me. Okay, if not, thank you very much. Look forward to see you all next week. Thank you.
Thank you.
Yeah, thanks. Okay, thank you. You face problem? Okay. Thank you. Good night. Okay, thank you. I'm going to end the meeting. Thanks.